Hello. Today I'm working with the law of conservation of energy. I've got a problem here that I want to work my way through. I've got a rock climber on the face of a cliff wall, and let's suppose that they decide they're scared and they need some help, so they're going to fire a flare directly upward. And so the flare is going to go up, come straight back down. Okay, we wouldn't want it to really come straight back down because that would be problematic for the rock climber, but let's say close enough to straight back down that we're not going to worry about any sideways motion. So the flare goes up, falls back down, and of course then the flare will end up landing at the base of the cliff. And I want to figure out how high up was the climber when the flare was fired based on the starting and ending speeds. Now, I've started a drawing over here on the left, and I'm just going to finish this up. Of course, I always like to make a little drawing first. But the first thing that I want to do is I'm going to just to finish this drawing, I'm going to just draw here. This red thing is the flare, and it's going to go straight up, come straight back down, yay, and then it'll crash down there at the bottom. Now, what I know is, going back to this picture, I know that here at the location where the rock climber fired the flare, I know something about the speed there, and it's at that spot that I want to know about where is the rock climber. So that's going to be one of the two places I want to think about. Let's keep in mind, whenever we're using the law of conservation of energy, we're comparing the total amount of energy at one place versus at another place. So I'm going to call these places A and B. So I'm just going to label this first place as place A. So rethinking that question, how high up was the climber when the flare was fired, what I'm trying to answer now is, what is the height of the climber at location A? So I'm going to need to compare that now with some other place. And since I do know that the flare reaches the bottom of the cliff with that particular speed, then I'm going to choose to think about the landing spot as my location B, because I have some information also about energy there. So those are going to be my two locations, A and B. And so you can see over on the right, I've set up space to make a little set of bar charts, because of course you know that I like to make bar charts to help me figure out what equation am I creating here. Now, before I can actually come up with any kind of numbers or amounts even on a bar chart, I need to make some decisions about where do I want my zero height to be. So I'm going to go with what I hope seems to you like the simplest solution. I'm just going to say that here at the height of the base of the cliff, that's where height is going to be 0. Now, that'll be handy, because then as soon as I find the value for height at location A, well then the distance above the bottom of the cliff is exactly equal to that position, so I won't have to do any unnecessary math at the end there. So, okay, let's make some bar charts to figure out then the solution to our problem. So at position A, I need to think separately about kinetic energy and potential energy. So did the climber have any kinetic energy? Sorry, I don't mean the climber, I mean the flare. So did the flare have any kinetic energy at location A when it was fired? We don't want to compare before firing versus after firing, because then we would have other energy transformations happening with the flare gun, and that's unnecessarily complicated. So we're just going to think about it leaves the flare gun at 22 meters per second. That's the numbers we're going to concern ourselves with at position A. So position A really is upon the flare leaving the flare gun. So to answer the question, does it have any kinetic energy? Well, heck yeah, it's moving pretty fast. It's moving 22 meters per second. So there is definitely going to be some amount of kinetic energy when it is at position A. So I'm just going to make a little bar there. Now, is there any potential energy at location A? Well, I make my decision about does it have potential energy based on is it somewhere other than a height of 0, and the answer to that is definitely yes. So the kinetic energy, yes, there is some because it's moving. The potential energy, yes, there is some because it's above the zero height. And so I know then that there's going to be some other amount of potential energy there. Now, as the flare rises and falls, well, as it rises, the kinetic energy bar would be shrinking while the potential energy bar grows at the same rate. And then as it falls back down, just the opposite, the kinetic energy bar would be growing at the same rate that the potential energy bar is shrinking. But now by the time it goes all the way up and comes all the way back down to B, well, at B, does it have any kinetic energy? Lots, because it's moving fast there. That's its very, very, very fastest. So at location B would be where it has the most kinetic energy. And potential energy at location B, I know that's going to be 0 because I decided that that's where the height of 0 is. So that's going to be a 0. And now, just thinking about making that equality work out, then I know that the kinetic energy at location B has to equal the total of those two bars for location A. So actually, I'm just going to do this the easy way. And of course, I already did it the hard way. So now I'm actually going to do this the easy way. And there. And now I know that it even looks just right, where the total on the right and the total on the left are going to be the same amount as each other. So now if I want to actually answer this, though, I need to do better than just make a bar chart. I need to actually start working with some numbers. So I'm going to do that right now. Now, kinetic energy at location A, to answer that, I would take half times the mass times the velocity at A squared, plus potential energy at A would be mass of the flare times little g, which I never said that it was on Earth, but I think that's a pretty fair assumption. So let's assume little g then is 9.8 meters per second times the height at A, and that's equal to half times the mass of the flare times the velocity at B squared, plus the potential energy at B is 0. Now, at that point, I can insert my numbers for velocities. I want to solve for y at location A. And by now, you might be thinking to yourself, but wait a minute, you didn't say anything about the mass. I didn't write anything about the mass of the flare there. And so, not knowing the mass of the flare, I don't actually know like how many joules tall is this bar, how many joules tall is this bar, how many joules tall is that bar. I don't actually know a number of joules for any of these. But even though I don't know an actual number of joules for either of them, that's not going to stop me from solving this. First of all, if you look at the blue mass that I have there, the mass appears in every one of those terms. Now, there are two ways you can go here. One, knowing that the mass shouldn't matter, and way back to our studies of kinematics earlier in the year, we know that the mass shouldn't affect how fast something is moving after it falls however far. So if the mass is irrelevant, well then you can make up a mass. Now, if you're making up a mass, then your number of how many joules is going to also be just a made-up nonsense number, but it'll help you solve the problem. Now, I actually personally don't prefer to insert a made-up mass, but if that's what works for you, then by all means do it. I, on the other hand, am happy to just work with not actually knowing a number of joules. Every term has m in it, so what I can do is I can just divide both sides of the equation by m, and once I've divided out the m, well then now I've got half times the velocity at A squared plus little g times the height at A equal to half times the velocity at B squared, and that's that. Now I know velocity at A, I know velocity at B, so I'm ready to solve. The velocity at location A was 22 meters per second, and the velocity at location B is going to be 30 meters per second. And you say, wait a minute, it's negative 30 meters per second. And I say, you're right, and I don't care. And the reason why I don't care that the velocity is actually negative 30 meters per second is I'm squaring it. And really, kinetic energy doesn't care about velocity. Kinetic energy just cares about speed. And the speed is 30 meters per second, whether the velocity is positive or negative. And squaring helps me not need to care. So I do half times 22 squared, and I get 242. Now the units of that, it's not joules since I divided the masses out. These are not numbers for energy, but meters over seconds. I square that, I get meters squared over seconds squared. And when I square 30, when I square that 30 number, then I'm going to get 450 meters squared over seconds squared. And now, in order to solve for that height at A, well then, to get y sub A all alone, then I'm going to need to subtract that 242 over to the other side. So 9.8 meters per second, algebra, 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 equals, subtracting gives me 1. What's wrong with me? So when I actually do that, then 450 minus 242 gives me 208. Now the units on that, still meters squared over seconds squared. And then to solve, I just divide by the 9.8 meters per second squared, which gives me 21.2. Now units, I take meters squared over seconds squared, and I divide meters over seconds squared. Well, the dividing by seconds squared is going to divide out. Meters squared divided by meters leaves me with a unit of meters. And, well, that makes some sense to me because what's the height is the kind of number that I would expect to see written in meters. So it makes me happy to see it that way. Now, if you wanted to, I've got my answer here. The height is 21.2 meters. And so, oh, hey, I have actually accomplished the mission of answering how high up was the climber. That climber was at a height here of 21.2 meters. So yay. Now, if you're really bothered by not having joules, well then you could go ahead and insert some numbers here for these masses. Just, of course, use the same mass in every spot, and you'll have some number of joules written down. And how many joules would depend on what mass you picked, but you can work it out for yourself. I'm not going to do it now, but you'll get exactly the same result. So there we have it, using the law of conservation of energy, just with gravitational potential energy for now, using a little bar chart. Hope you enjoyed it. It was the best time I've ever had. Thanks, and I'll see you later.